Video 63 of the master course Quantum Chemistry of Molecular Electromagnetic Properties. The topic of this lecture is Multi-Configurational Self-Consistent Field Method. The Multi-Configurational Self-Consistent Field Method, or in short MCSTF, is a generalization of the Hartree-Fock method, which means we still optimize the orbitals, but now it's not a single determinant wave function, but it's a multi-determinant wave function for which we optimize the orbitals. So the MCSTF wave function is a linear combination of some Slater determinants, where we have here the expansion coefficients. Sometimes, or often, it's actually not Slater determinants, but it's linear combinations of Slater determinants which are used, which are the so-called configuration state functions. A configuration state function is a symmetry or spin adapted linear combination of a few Slater determinants. Because every Slater determinant, of course, is an eigenfunction of the Z component of the total spin operator of the electrons, but it's not necessarily an eigenfunction of S squared, capital S squared operator. So they do not necessarily have a proper spin. And therefore one makes small combinations of the necessary Slater determinants in order to get a combination of Slater determinants which is spin adapted. And these kind of spin adapted, we can also do it for symmetry adapted combinations of Slater determinants are then called configuration state functions. So one can expand the MCSTF wave function either in just determinants or in these configuration state functions. Now, as I said, in MCSTF, one not only optimizes these configuration or Slater determinant expansion coefficients, but one still also optimize, like in Hartree-Fock, the molecular orbitals, meaning the molecular orbital coefficients. MCSTF, like Hartree-Fock, is a variational method, and therefore we determine the best values of both the molecular orbital coefficients as well as these determinant or configuration state function coefficients by finding the stationary point of the energy, meaning we take the derivatives of the MCSTF energy with respect to all the molecular orbital coefficients and the derivatives of the MCSTF energy with respect to all the configuration state function or determinant coefficient, set these derivatives to 0. This leads then to a large set of equations which one have to solve in order to obtain these coefficients. There's, however, also another way how one can write the MCSTF wave function, and that is given here. Here we start with some kind of a wave function, an MCSTF wave function, which is not the optimized wave function, and we let two exponential operators act on it. And these two exponential operators, these are two unitary transformations, they then allow us to get to the optimized MCSTF wave function. And there are two because we have to find the optimal values for the expansion coefficients in determinants. And for this we have the unitary transformation with the S operator here, where the S operator is the sum over all what is called state transfer operators, which means that we transfer this state to some other linear combination of determinants. And the S and 0 here, these are the expansion coefficients. And the second part, that's the change of the orbitals, where we have here the operator kappa, and the kappa is the sum over all orbital rotation operators, where we here rotate P into Q or Q into P, and kappa, again, the expansion coefficients. This kind of ansatz for the to be optimized wave function with the unitary transformation can actually also be used for the Hartree-Fock wave function, where of course then we only have one determinant, so the part with the S operator vanished, but we still have the part with the orbital rotation operators, where we here have some single determinant And then we let act with this unitary operator. By the way, because this has to be unitary, which means it keeps the norm of the wave function. And that means that kappa itself has to be anti-emission, which explains the minus sign here. So here we have now the again the orbital rotation operators. And here for the Hartree-Fock case, we only have replace occupied by virtual orbitals, because um, rotations between two sets of virtual orbitals vanish if we start with one determinant where we only have occupied orbitals. And rotation between occupied orbitals, they don't change the total wave function because it corresponds just to making linear combinations of the columns in the Slater determinant, and that doesn't change the value of the Slater determinant. Now, the advantage of this way of writing the SDF wave function is that because this is a unitary operator, so if our original SDF determinant is normalized, then the norm is preserved by the unitary transformation. So we don't have to think about more of keeping the wave function normalized.